Hello everyone. Hello everyone. Today we'll start electromagnetic induction. In this topic, mainly we have to focus on the key points: magnetic flux, Faraday's experiments, Faraday's laws of electromagnetic induction, Lenz's law and law of conservation of energy, expression for induced EMF based on both laws, method of producing EMF by changing magnetic field, by changing the area of the coil, by changing the relative orientation of the coil with magnetic field, eddy currents, self-induction and self-inductance, mutual induction and mutual inductance, and additional information. Now let us see what is meant by magnetic flux. Magnetic flux through any surface is the number of magnetic lines of force passing normally through that surface. It can also be defined as the product of the area of the surface and component of the magnetic field normal to that surface. We consider here surface area ds. Let n cap be unit normal vector to the surface and b bar be the applied magnetic field. Let theta be the angle between n cap and the applied magnetic field vector b bar. The magnetic flux linked with any surface is given by dot product of magnetic field and area vector. That is, d phi is equal to b bar dot ds bar. Direction of ds bar is along the normal to the surface and n cap is unit normal vector. It can be simplified as d phi is equal to b ds cos theta, where b is the magnitude of applied magnetic field, ds be the magnitude of area, and theta be the angle between n cap and b bar. For total area A, the magnetic flux or total magnetic flux linked with total area is given by dot product of magnetic field into area vector, which can be simplified as phi is equal to BA cos theta. The magnetic flux is positive when the theta lie between first and fourth quadrant, that is, theta is equal to or greater than 0 or less than 90 degree, or when theta lies between 270 degree and 360 degree. The magnetic flux linked with any surface area is 0 when theta is equal to 90 degree and theta is equal to 270 degree. That is, angle between normal to the surface area and applied magnetic field is 90 degree or 270 degree. The magnetic flux is negative when theta lies in third quadrant. That is, theta is greater than 90 degree and less than 270 degree. The flux is maximum when theta is equal to 0, that is, magnetic field is lie along the normal to the area. The magnetic flux across any coil depends on applied magnetic field, area of cross section of the coil, and the angle between magnetic field and normal unit vector. That is, the magnetic flux across a coil can be changed by changing the strength of magnetic field B, the area of cross section of the coil A, the orientation of the coil with magnetic field, that is theta, or any of the combination of the above. Magnetic flux is a scalar quantity. SI unit of magnetic flux is Weber or Tesla meter square. CGS unit of magnetic flux is Maxwell. 1 Maxwell is equal to 10 raised to minus 8 Weber, and Magnetic flux associated normally per unit area is called magnetic flux density or strength of magnetic field or magnetic induction B. Now let us explain the Faraday's laws related to electromagnetic induction. The Faraday's first experiment, which is also known as coil magnet experiment. In this case, we are using one coil across which galvanometer is connected and one bar magnet. When the north pole of the magnet is When north pole of magnet is moved towards the coil, the galvanometer shows the deflection towards right hand side. That is, when the relative motion of the magnet with respect to coil is done, some current is flowing through the coil. Similarly, when we move the south pole of the magnet towards the galvanometer shows deflection in the opposite direction, that is to the left hand side. Here one more explanation. When we move the magnet inside the coil, the current will be increases. The to and fro motion of the magnet towards and away from the coil shows the deflection in opposite direction. When we move the magnet towards the coil, it can move towards the right hand side, while we moving the magnet away from the coil, the deflection is showing in the opposite direction, that is left hand side. Here when we move the magnet towards the coil, the galvanometer is showing deflection. Once again you see this. Slowly we are moving. That time the magnetic flux linked with the coil changes relative to the position of the coil and the magnet due to the magnetic lines of force cutting at the different angles at the same cross-sectional area of the coil. Once again see, magnetic flux linked with the coil changes relative to the position of the coil and the magnet due to magnetic lines of force cutting at different angles at the same cross-sectional area of the coil. Now we can make the few observations on this magnet coil experiment. The relative motion between the coil and the magnet, the induced polarities of magnetism in the coil, in the direction of current through the galvanometer and hence the direction of in the galvanometer, that the induced current is available only as long as there is a relative motion between the coil and magnet. The coil can be moved by fixing the magnet, or both and coil and magnet can be moved towards each other or away from each other. There must be relative velocity between coil and magnet. Magnetic flux linked with the coil changes relative to the position of the coil and the magnet. Current and hence deflection is large if the relative velocity between the coil and magnet and hence the rate of change in flux across the coil is more. Here we'll see the another one experiment, Faraday's experiment 2, which is known as coil-coil experiment. In this case, across first coil, primary coil, we are connected a battery of EMF E, where across the secondary coil or second coil, we are connecting the galvanometer to measure the current. Now when the key is closed, what happens here? When the primary coil is closed, current grows from 0 to maximum value. During the period of changing, the current induces changing magnetic flux across the primary coil. This changing magnetic flux is linked across the secondary coil and induces EMF in the secondary coil. Induced EMF and hence the deflection in galvanometer lasts only as long as the current in the primary coil and hence the magnetic flux in the secondary coil change. When the primary circuit is open, current decreases from maximum value to 0. During this period, changing current induces changing magnetic flux across the primary coil. This changing magnetic flux is linked across the secondary coil and induces current in the secondary coil. However, note that the direction of current in the secondary coil is reversed and hence the deflection in the galvanometer is opposite to the previous case. So, we can conclude the Faraday's laws of electromagnetic induction as: first law states that whenever there is a change in the magnetic flux linked with the circuit, an EMF and hence a current is induced in the circuit. However, it lasts only so long as the magnetic flux is changing. Second law, it states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with a circuit. Mathematically, the EMF is directly proportional to change in flux with respect to time. Once again, we can focus on the first law. Whenever there is a change in the magnetic flux linked with a circuit, an EMF and hence a current is induced in the circuit. However, it lasts only so long as the magnetic flux is changing. Similarly, the second law states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with a circuit. EMF is directly proportional to d phi by dt, that is change in flux with respect to time. So we can write down E is equal to k into d phi by theta, where k is proportionality constant. The change in flux is given by phi 2 minus phi 1 by t, where k is constant and units are chosen such as k is equal to 1. Now let us focus on the Lenz's law. The direction of the induced EMF or induced current is such that it opposes the change that is producing it. If the current is induced due to motion of the magnet, then the induced current in the coil sets itself to stop the motion of the magnet. If the current is induced due to change in current in the primary coil, then the induced current is such that it tends to stop the change. Lenz's law and law of conservation of energy. According to Lenz's law, the induced EMF opposes the change that produces it. It is this opposition against which we perform mechanical work in causing the change in magnetic flux. Therefore, mechanical energy is converted into electrical energy. Thus, Lenz's law is in accordance with the law of conservation of energy. If, however, the reverse would happen, that is, the induced EMF does not oppose or aids the change, then a little change in magnetic flux would produce an induced current, which would help the change of flux further, thereby producing more current. The increased EMF would then cause further change of flux and it would further increase the current and so on. This would create energy out of nothing, which would violate the law of conservation of energy. Expression for induced EMF based on both laws. E is equal to minus d phi by dt, or E is equal to minus change in flux, that is final EMF, final flux minus initial flux phi 1 by t. And for n number of turns of the coil, E is equal to minus n d phi by dt, or E is equal to minus n into phi 2 minus phi 1 by t. Expression for induced current is given by I is equal to minus d5 by r into dt. Expression for charge dq by dt is equal to minus d5 by r into dt. dq is equal to minus d5 by r. Induced EMF does not depend on resistance of the circuit, whereas the induced current and induced charge depend on resistance. There are some methods of producing induced EMF as follows: by changing the magnetic field. The magnetic flux phi can be changed by changing the magnetic field, and hence EMF can be induced in the circuit as done in Faraday's experiments. Second method is by changing the area of coil A available in magnetic field. Magnetic flux phi can be changed by changing the area of the loop A, which is acted upon by the magnetic field, and hence EMF can be induced in the circuit. When we move the rectangular coil in the applied magnetic field with velocity v, the loop PQRS is slided into uniform and perpendicular magnetic field. The change in area of the coil under the influence of field is dA in time dt. This causes an increase in magnetic flux d phi. Therefore, we can give the magnetic flux according to definition B into area dA. Now the area is nothing but it is the area of rectangle having length L and breadth V dt. Therefore, we can substitute dA is equal to L into V dt. Therefore, E is equal to minus d phi by dt. If you differentiate the equation, we will get E is equal to minus BLV. The induced EMF is due to motion of the loop, and so it is called motional EMF. If the loop is pulled out of the magnetic field, then E is equal to BLV. The direction of induced current in anticlockwise in the loop, that is P dash S dash R dash Q dash P dash, by Fleming left hand rule or Lenz's rule. According to Lenz's law, the direction of induced current is such that it opposes the cause of changing magnetic flux. Here, the cause of changing magnetic flux is due to motion of the loop and increase in area of the coil in the uniform magnetic field. Therefore, this motion of the loop is to be opposed. So the current is setting itself such that by Fleming's left hand rule, the conductor arm PS experiences force to the right, whereas the loop is trying to move to the left. Against this force, mechanical work is done, which is converted into electrical energy. If the loop is completely inside the boundary of magnetic field, then there will not be any change in the magnetic flux, so there will not be induced current in the loop. Let us see the statement for Fleming's right hand rule. If the central finger, forefinger and thumb of the right hand are stretched mutually perpendicular to each other, and the forefinger points the magnetic field, thumb points in the direction of motion, then the central finger points to the direction of induced current in the conductor. Once again you see, if forefinger indicates magnetic field, thumb indicates force, and middle finger indicates electric current. If the central finger, forefinger and thumb of the right hand are stretched mutually perpendicular to each other, that is thumb, forefinger and middle finger, they are at right angle to each other, then the forefinger points the magnetic field, thumb points the force or direction of motion, then the central finger points the direction of induced current in the conductor. This is known as Fleming's right hand rule. And the one more method, by changing the orientation of coil in the magnetic field. The magnetic flux phi can be changed by changing the relative orientation of the loop with the magnetic field B, and hence can be induced in the circuit. This is the applied uniform magnetic field B. This is the rectangular coil PQRS. N cap be the unit normal vector, theta be the angle between N cap and B bar. Here phi is given by NBA cos theta. At a time t with angular velocity omega, theta is equal to omega t, that is at t is equal to 0, loop is assumed to be perpendicular to the magnetic field and theta is equal to 0. Therefore phi is equal to NBA cos omega t. Differentiate this equation with respect to time, we can get d phi by dt is equal to minus NBA omega sin omega t. But the induced EMF is given by rate of change of magnetic flux with respect to time, that is E is equal to minus d phi by dt. Therefore we can put the value of d phi by dt, we can get E is equal to NBA omega sin omega t, which is in the form of E is equal to E0 sin omega t, where E0 is equal to NBA omega is maximum EMF. The EMF changes continuously in the direction with respect to time, giving rise the alternating EMF. See how the EMF changes continuously in magnitude and periodically with respect to time, giving rise the alternating EMF. This is the pictorial representation for this. We can see the equal time intervals. Along y-axis we have taken the EMF, and across x-axis we have taken theta. If initial position of the coil is taken as 0, that is normal to the coil is at 90 degree with the magnetic field, then theta becomes theta plus pi by 2 and or omega t plus pi by 2. The expression for EMF is given in terms E is equal to E0 cos omega t. That time the variation of E with respect to time is given as shown in this diagram. So alternating EMF and consequently alternating current can be expressed as sine or cosine functions. This method of inducing EMF is the basic principle of generators. So in the next class we will see eddy currents and Coles current. Thank you.